Okay, I think we can start. Hi everybody, this is another session of our PhD seminars. She is our end of the second year student, Gaurvi. She's gonna present us her work, which is the Invariant action recognition. So she's gonna talk about it more. So thank you.
Thank you, Luca. The topic of my presentation is view invariant action recognition. What is view invariant action recognition? What we want to do is we want to understand what property of an action makes it that particular action, and independent of whatever viewpoint it's observed from. And we want to do it using only 2D video information without depth, mocap, anything else, but RGB video information. And to do this, we can either build features that are invariant to the viewpoint from which they are built, or we could make systems that can learn, automatically learn features that are view invariant, and then apply them to other systems. And we want to use these features, built or learned, in a system that can then learn new actions and new data sets, ports to new information with minimal effort. To do this, the starting point of the entire work was this data set called Cooking Actions. It was recorded in this facility by Alicia Vignolo. It is simple upper body actions seen from 3 different points of views: front, lateral, and egocentric, varied, non-symmetrical viewpoints, controlled illumination indoors, no background clutter, black background. It's simple overall in terms of excess distractions. The biggest important point is that it has the possibility of clear splits between viewpoints. That is, it is possible to separate all viewpoints and then compare each other for every action, and there is uniformity there. Or train on some, test on others. There's clear separation. Now, there were so the first approach was building view invariant features. For this, we used shared-let transform, which was being used at the time. There was work going on here, so we tried to apply spatiotemporal features derived from this transform on this particular data set, and we noticed that it did show invariant properties. It was firstly able to discriminate between actions, which it hadn't been applied to at all till then. And the second point was it was able to club together videos of actions seen from different points, the same action seen from different points of view. It was able to club them together. So it did demonstrate view invariance and action recognition properties, and it led to a publication in iChap last year. And so from this, the train of thought ensued that can a neural net learn these features that we had calculated and use them? But then, could a neural net learn completely new features that were view invariant? Has it been done? So we looked into the literature available at the time and built a state-of-the-art on this. And so we moved on to our next approach, which was learning view invariant features. And the state-of-the-art at the time can be divided into 2 parts. There was a set of action recognition systems, which were deep learning systems, so based on deep learning, and they had high recognition accuracy on general large data set action data sets like UCF 101 with 101 labels, or HMDB 51 with 51 labels. But then we tried to implement these systems on multi-view data, and we noticed that the accuracy decreased drastically. The other kind of action recognition systems that involve neural nets were the other way around. They used handcrafted features that were built specifically for the use in viewpoint, for their property of robustness to different viewpoints. And then these were fed into a deep network. And while their accuracy on such systems, on such data sets was very high, but they required excessive amount of pre-processing before being fed to build the features, before being fed into the deep network, or they required other modalities, depth, mocap information, which we didn't want to use. So there wasn't systems that were learning view invariant information, so in the general literature. So we moved, but with deep networks in general, the more complex a system is, the more complex a task is, the bigger the network needs to be. And the bigger the network needs to be, the more amount of information it requires to train it. And for the kind of research that we wanted to do, the problem that we had to solve, the databases that were available weren't very large, while something like this would require a huge amount of information. So the solution was to use a complex pre-trained network. Simple ones already exist, like VGG and others, but a more complex one was needed. So we looked at these pre-trained networks that were available, especially for action recognition. And luckily for me, this Inception 3D had been released pretty recently. With a comparative analysis to the others that had been released that were available, this was the best one we found, so we picked this. So Inception 3D, or i3D, it is based on the Inception version 1 model, which was released in 2014, and it won the ImageNet challenge that year. It is a image model for classification and detection. And they used this in a more 3D environment. I will come to how they used this to make the i3D in a minute. First thing I want to mention, so this is the general schema for Inception and Inception 3D. These are the number of layers. It has 17 layers. And they trained it in 2 ways, one using RGB information and the other using optical flow information. And they got results from both, and when they added them unweighted, they got even better results. So we have 3 modes of use that we'll be talking about using later: RGB, flow, and joint. Coming to how they made this model. Well, they took the Inception version 1 and first trained it on the ImageNet. ImageNet dataset is huge. It has 21,000 labels and 14 million images. And so first the Inception version 1 model was trained on this, and we have a pre-trained network. But this is still an image network. You have a lot of filters that are 2-dimensional filters, 3x3, 5x5 convolutional filters. But then they took each of these, let's say a 3x3 filter, and they replicated it 3 times. So we have a cube, so a 5x5 would be 5 times. And then used this inflation was then called the Inception, the i3D model. This now understands images. The Inception model understands everything about images that could be learned in theory, probably. And then they trained the inflated model on the kinetics action dataset, which was released around the same time. The kinetics action dataset is the largest dataset for actions that is available today. It is taken from YouTube, clippings from YouTube videos, and it has 400 classes, and each class has more than 400 clippings. So what it has learned at this point could be a very large amount of things to learn from videos. So we wonder, of all the things that it has learned, has it also learned something that might lead to something that is view invariant in actions? So to test something like this, first thing that we realized was that the data set we had would not be able to even fine-tune this kind of a data set, this kind of a model. So we looked into literature, we tried to find a bigger action data set which still fit our paradigm. So clear separation between different viewpoints, a multi-view data set of course, and that also had not too much other movement, overall not too similar. And what we used was this one. It has also high number of repetitions. So firstly, high number of comparatively not very high, but still higher than others, number of videos per action and number of repetitions per actor, separate videos, so that it was able to learn. So we have 10 different classes and 1400 videos in total. So we use this for the rest of the work. Coming to experiments. Now, we have this very large model, but how do we glean information from it? Because to begin to start to set this up was something that had to be decided. How do you get information out of it? So the first experiment we ran was very simple. We took this data, this entire model, the way it was, with set up for 400 classes, and we gave it the Northwestern UCLA multi-view data. So the name of the data set, Northwestern UCLA multi-view 3D data set, but it's a 3D data set, but we are only using 2D information, only video information, and I'll continue calling it UCLA data set because it's a very long name. One point to be noted here is that the classes that are in the UCLA dataset and the 400 classes of kinetics, there is no overlap. There are no matches. I mean, 400 classes, you think one would match, but so we gave the input of the UCLA dataset and looked at what the model did. A point to be noted here is that in the Inception 3D model, so in general, most deep networks have a fully connected layer at the end. But what they did was they replaced it with a simple average pooling and convolutional layer. So they tried both things. They noticed that the difference wasn't much, but computationally it was much less heavy. So they made this change. And so at the end, for this experiment, there are neurons being activated. Every time that we are only looking at which neuron has the highest activation when a specific video from the Northwestern UCLA dataset is input. And this is what we get. On the x-axis, we have all the labels from the UCLA dataset, and on this axis we have the neuron that was activated the most. And any neurons that were activated very little were discarded. And this is in percentages because the number of videos per class were varied. So this is the percentage distribution. For example, the donning, which by the way means putting on a garment, I had to look that up. It's 30% of the times it activated neuron number 51, for example. And so this is the results we got. What you notice is out of 400 classes, only these neurons were activated often. And then they were activated quite often because 24% times the same pickup with two hands went for the same neuron. And there are only these many out of 400. So we noticed that the system was able to pick up a few things even though it hadn't been trained at all on these inputs. The next thing important, this is for the flow stream. And we tried it for the other two streams, that is the RGB and then the joint. And what we saw was this. For the RGB stream, only 3 neurons were activated, and 1 neuron was activated more than 80% of the times for every action. So we see that maybe the RGB doesn't pick up a lot of information for this data set. And when we tried it on joint, it looks very similar, but it is actually different. I just compared values because it looks identical. But it is heavily weighted. So it probably sees it with very high concentrations that it is that action. Which for it actually happens to be clapping action. It didn't seem that way, but apparently it just thinks they're clapping all the time. Next thing we tried was, instead of looking at the output at the predictions, we looked at it a little before. So one classifying layer less, because the last layers are usually classifying layers. One layer less, we extract the outputs here, and we take these outputs and then we cluster them using k-means, just to see what happens, what is the result going, what is going on here. So we cluster them using k-means into 10 clusters, simply because there are 10 classes, and these are the results. Same thing, x-axis we have labels, and y-axis we have clusters, and percentage distribution. What we see is the following. There are definite clusters, there are high values, and similar actions were clubbed together. For example, sit down and stand up were clubbed together. So the model sees, okay, they seem very similar, and so it gets confused. But it sees that it's still 33%, 36%. So there is some amount of accuracy. Donning and doffing, so putting on a clothing, taking it off, are clubbed together. Walk around and carry. So carry probably involves walking. So it again gets them confused, but there are clusters. It clusters them together.
Can I ask you a question?
Yeah.
So the column here sums to 1.
Yes.
Also to 100 or whatever, right?
Yes, 100. This is,
in some cases, there's
quite a lot of concentration, right. And this is without any training. This is without any change.
You don't supervise the clustering.
Yeah. And even for lower values, they're still not very low. At this point, we tried to pick up one cluster per class. So we used the Hungarian algorithm to pick one of the highest. And what we got was this. The highest value we got was 48% for donning, one cluster, and the lowest of all, if we pick up the highest per one, is 17%. So if they were randomly classified, that would still put 10% accuracy, let's say. But the lowest that we got was still 17%. So there is still definitely some good results. I mean, the system is actually able to get something out of it. So overall conclusions for this knowledge testing is that the model was able to separate actions that it had never seen before. The feature extracted from the middle could also be helpful, but the exact point of extraction we haven't settled yet. We could change things and look at try other things. And similar actions were difficult to separate at this point, but probably with some training that could improve. So now we move on to the training experiments. Some things I want to clarify beforehand about these. Firstly, we're looking at accuracy only, because it's more quantifiable, I guess, at this point. Top 1 and top 2. So top 1 means the percentage of times the correct class was the top choice for the system, and top 2 is when the percentage of times the correct class was in the top 2 choices. This is done also because there are similar pairs, and we want to see what happens. We only look at flow, optical flow inputs and the optical flow stream for the reasons I've said before. But we might move on to RGB at a later point. And the input data set, Northwestern UCLA, was split into 3 parts: training, validation 1, and validation 2. Now, validation training is this. In this table, here we have all the actions, the number 1 to 12, but then 2 of them are missing. That's how they named it initially. And V1, V2, V3. The blue ones are the training. They're from 2 viewpoints and 8 actors. Then we have validation 1, which are these two actors, these two viewpoints. So we have unseen actors here, unseen subjects, and the red ones are is validation 2, which is unseen viewpoint, which also happens to include two unseen actors. The highest accuracy for this and the state of the art is 75% for this split particularly, but they also use this part for training. So the first fine-tuning training, the simplistic thing possible, we simply replace the last end with 10 outputs instead of 400 and fine-tuned it, and this is the part that was trained. But you see, the line is going in the middle of this layer. How do you train half a layer? Well, this is the inception module, which are littered all through the model, and an inception module actually looks like this. We have 7 different parts and then concatenated 4 different streams, which become smaller, and then they're concatenated and put back into the network. And this is what made Inception so very good at what it does. And we trained only half of this. So we tried different things, and this is the one that was optimal. And after fine-tuning this, these are the results we get. So I could tell you which color means what, but I don't think it's useful. We have this is top 1 accuracy, top 2 accuracy, and the highest value that it gets to is 38% training, 38, approximately 38% for all 3 cases in so training, validation 1 and validation 2. And what we see from this is, okay, it didn't get very high, the values weren't a lot, but at the same time, the validation 2, which is the training, the unseen viewpoint, very closely follows the original training. And that means that this data set, this model definitely picks up view invariant features. For it, it is the same to classify something that it's trained on and something that it hasn't seen, the viewpoint it hasn't seen. So this is very promising. This is the first time we got any results pertaining to view invariant. The top 2 accuracies go up to 47% training and 46.8% for validation 2. There it's 38%, 38.6, 38.9, and 38.0. All the graphs were smoothed by 60%, by 0.6, factor of 0.6 automatically by TensorFlow. The second experiment was, in general, as I mentioned before, a lot of times, no, very, very often, neural nets have fully connected layer at the end. So I thought, let's try this. Let's try a fully connected one. So we replaced the last layer, the classifying layer, with a fully connected, and other than that, it was the same, and we trained it. And these are the results we got. We went up to the 49.4% training accuracy and a 48.2% validation 2 accuracy for top 1. And they're still pretty close together. In case of top 2, it's 56% training accuracy and 56.2% training accuracy, 56.0 validation 2 accuracy. And again, they're following really well. And so at this point, we thought these are very, very highly trained features. What if we move back a little? We lose some of the original training. We need less processing. And what if we get to a more raw data? So we moved back 1 step. And we took from mix 2B instead of mix 3B and did the same exact thing. And what we got was this. So the training accuracy has gone up to 89%. And the validation 2 accuracy is 75%. And if you remember correctly, that's the state of the art. But at the same time, there is a big difference now. There is a 14% difference between training and validation. So we lost how closely it was able to follow, but at the same time, But if you see the top two, then they are closely together. There's 96% and 93%. So we see that when it sees a new viewpoint, it gets confused between two similar ones, and it misclassifies those the two similar between them. It gives them the wrong labels between each other. So the top two accuracies are still very high. These are the results I got very recently. And there's another one more experiment I tried, which was, well, increase a node, try to see what happens, and the accuracy is increased a little more. So training went to 90, but down a little, but the validation went to 77%. And this is something I just did the last week, and it is undigested. I haven't really figured it out yet, but this is quite promising. And there is seems to be a trade-off between robustness to new viewpoints and overall accuracy. There is overfitting happening. We still have to try more things, try classical classifiers. There's a lot more to be done. And this is in the middle of the work. And we're still gauging how view invariant are the features, and there is still a lot to be done. Basically, we also trying to try training on one viewpoint or trying RGB information. So in a few months, I'll let you know what happens. Thank you. Any questions?
Maybe you said it and I missed it because I was out for it. Or maybe you said at the beginning and I lost it. So my understanding would be that some of the action would require maybe happen over a wide range of time. So this is something that was taken care in some sense during training. For the recognition, for the action classification is done sort of at a fixed base, and then so how does it happen?
So there are multiple ways to do this in this model. It is designed so that different frame amounts can be taken. But in the case that we've done it here, we give it the entire, so it's a clipped, trimmed videos, and we give it the entire one. And then the feature has a variation, a small variation, and it picks randomly for the training.
And then the classification is one shot, so it's
yes.
sitting.
It takes any cropping of that and tries it.
Okay. So there is no time. It's not done over time in a sense. So
no, it doesn't do any aggregation of any sort. But a lot of the components still goes, because the variation after the feature extraction in that dimension was like from 2 to 4. So we picked up any 2 from that.
Would it make sense, or would you plan in the future to take
any well, because they are already very small, okay. So there isn't much scope, but if we can find some longer videos, it might be possible.
Okay.
At this point, it is too short. Yes.
So, again, maybe I totally missed that, but so you use most of the pre-trained model, and you focus only on training the last one. Okay.
Yes.
So the first attempt, it was the very first one that we saw, not the fully connected, before the fully connected.
More. Yes.
Okay,
no,
so
no, I'm sorry, one more. Before the fully connected, yes?
It's just this one. So they just retrained all the tiny part.
Uh-huh.
Oh, okay.
So actually, initially when I tried training this, it was taking about 5 hours per epoch. So it took about 5 days for one time. And so what we did was we extracted features here and then trained only this section.
Okay. And
then it took about 20 minutes for the initial experiment and about 4 or 5 hours for the last experiment. So.
Okay. And on another curiosity, you choose this kind of model, but are there any other pre-training model you can use? Or,
Yeah, I found another one that was good, but I don't remember the name at this point. I can look it up and tell you. There was one more that was close. Any other questions? Thank you.
Thank you so much.